Okay, good morning, everyone. I hope you can hear me clearly and can see the screen also clearly. Can somebody kindly respond?
Yes, sir. Clear.
Yeah, thank you. Okay, see, I always, every day you might have noticed, I always ask whether you can hear me clearly and can see the screen clearly, because there's no point in carrying on if you are not. Okay, I might as well be then talking to a blank one. Okay, it's for your this thing advantage that you hear me clearly and can see the screen. Sometimes, of course, the internet plays up either on your end or my end, and that's not in our hands. Okay. So please, whenever I ask if you can hear me clearly and can see the screen clearly, any one of you all, please come up. Don't wait for the other person. Just come up and just say. So just one answer if I get is more than enough, and then I can continue. Okay. Right. So a very quick recap on the cycloconverter that we started on yesterday. And as I said, there was just one small portion with regard to a question. We'll come to that, but let's have a quick recap. Cycloconverter is a synchro converter, but without the DC element. You're converting AC to AC, right? And also, when you're having a cycloconverter, we have to always note that the output frequency is always less than the input frequency. And the two types of cycloconverters that we discussed, single phase to single phase. Okay, I hope all of you all had taken the screenshots whenever I had requested you, because when the notes are going to be posted to the app, and when you look at those notes, then you may not find, you'll find everything blank. Okay, you will not have any of the arrows that I think. So then you will not be able to understand. So with those notes and those screenshots or photographs that you have taken of the screen, if you follow them and the notes, then you will be able to understand. And here we saw how AC was converted to AC without any DC element, and that the output frequency was half the input frequency. We were getting only one cycle of output as compared to 2 cycles of input. So we were getting half the input frequency, therefore meeting that requirement. What? Output frequency is always less than the input frequency. Then we saw the 3-phase to single phase. As I mentioned, the 3-phase to single phase, this single phase is one phase of a 3-phase synchronous motor. UVW, there are 3 phases in a motor. So it is going to be pertaining to one phase, and 3 phases are then be converting into one phase. So yesterday I showed you that you're going to have 3 such similar circuits, one for U, one for V, and one for W phase. Okay, so yesterday also we discussed this, how we were going to get current flowing first in one direction and then the current flowing in the other direction, resulting in one waveform as opposed to 3 input waveforms. So output was getting only one cycle as opposed to input having 3 cycles, and therefore the output frequency was 1/3 the input frequency. Okay, so coming to those questions, yesterday we discussed what is the blocking mode. If you remember, I said that when your positive converter is firing, your negative converter is blocked from firing, and when your negative converter is firing, then your positive converter is blocked from firing. If you allow both of them to fire simultaneously, then you would have a direct short circuit. Okay, so that is what is meant as the blocking mode. Very simple to understand that. And I retained this one for today because it requires a little bit of extra explanation and for you all to understand. To understand how we get this so-called internal circulating current or circulating internal current of a cycloconverter, or for that matter, any converter, even your synchro converter, we'll come to know the reason why. We saw that we were using thyristors. Yes, for in your synchro converter, three-phase converted into DC, and then after that, that DC was converted back into AC, again using thyristors. Even in your cyclo converter, we were using thyristors, the positive converter, and thyristors for the negative converter. Okay, for both single phase to single phase and three-phase to single phase. Okay. Now, to understand what is this internal circulating current, we must need to know what are the things that are going to stop the particular thyristor from working. So let's digress to the thyristor. A thyristor is denoted by this symbol. You have the anode, you have the cathode, and you have the gate. A thyristor will conduct as long as you have positive on the anode and negative on the cathode, just like a diode. Okay, but this diode is not going to conduct until and unless you're going to get a gate. Then afterwards, if you remove the gate, your particular thyristor will continue to conduct. If you're going to look at this diagram, okay, you are going to have a positive here, you're going to get a negative over here, and this particular setup, these are called back-to-back connections of your transistors. So no matter you put a positive here, because this is a PNP, okay, a PNP type of transistor here also, and this one is an NPN transistor. So it is a combination of this block, PNP and NPN. Okay, and until and unless, as you see, unless you're getting this gate, in other words, this transistor gets forward bias, that will automatically forward bias this transistor. Why? Is because this collector is connected to the base. So once this transistor gets forward bias, first this transistor gets forward bias, this one will automatically get forward bias provided there is a gate. And once you remove the gate, since both these are forward biased, they will continue to conduct till you remove this voltage and this voltage. In other words, you remove this plus and minus, then only this thyristor will conduct. So let's see the methods of stopping the thyristor, and then we'll take it from there. Right? Methods of stopping the thyristor from conducting. Okay, there are three methods. Okay, number one, by removing the forward bias, that is that positive and the negative that I told you. Okay, let me draw it here, otherwise I'll have to go up and down. Okay, so you have this, sorry. Okay, here's the thyristor. Okay, this is the gate. If you remove this bias, this positive and negative, the thyristor should stop conducting. Okay, no matter whether there is a gate or no gate. If you are not going to have a forward biasing for this thyristor should not conduct. By giving a negative gate pulse, okay, now we saw from that particular diagram, okay, this particular diagram, that this has to be a positive because NPN. And as I said, this transistor has to conduct first, then this transistor will conduct. So this will have to be a positive gate over here for this transistor to start conducting. A way to stop this transistor from conducting is to take off this and put a negative gate. Okay, and that will turn off this that particular transistor. If that transistor turns off, then the other one automatically turns on. So that is called as a negative gate or a gate turn off thyristor. Okay, so that is the second method of stopping the thyristor from conduction. The third means is by reducing the holding current to below the minimum value for conduction. Okay, let's go to this particular characteristic. Okay, this is when the thyristor will conduct if you're going to force it to conduct without a gate. So what are you doing? You're taking it to a very, very high voltage. And as you know, even if you're going to take a diode to a very high voltage, it is certainly going to start conducting. Okay. Instead of that, instead of taking it to a very high voltage so that it can conduct, we can make that same thyristor conduct at this particular point. So let's say this was around 1000 volts, okay, for it to conduct. We are using this, say, at about 100 volts, roughly. I mean, it depends from thyristor to thyristor. Okay. And at 100 volts, you're providing that gate. And by providing that gate, you're making the thyristor forward biased and thus conduct at a much, much lower voltage than this particular forward breakover voltage that they are calling it. This particular voltage is called the forward breakover voltage. So we are not interested in that. We are interested in this, thus making the thyristor conduct safely. This will be a possibility that your thyristor can get damaged, and therefore nobody does that. So what did we say? We can reduce the forward bias voltage. Okay, so if we take off this voltage, your thyristor, number one, should stop conducting. Number two, we said that if we take off the biasing, that was one of them. If we give the negative gate, your thyristor will stop conducting. The third thing for stopping the conductor to the thyristor from conducting is to reduce this holding current. There are two things called holding current and latching current. Latching current is different from holding on current, because once it is latched, it will keep conducting. But if it comes below this holding current point, your thyristor goes into a high resistance region and stops conducting. So three methods of stopping the thyristor from conducting. Number one, by removing the forward bias, that is by removing this positive and negative from the anode and cathode respectively, or by giving a negative bias here, okay, or a negative gate called a gate turn off. And the third one is by reducing it below the holding current level. Okay, right. So now we know that the thyristor turns on with those conditions. Now, what I'm going to draw here, and please pay particular attention. I'm drawing a sine wave. Okay, from a negative value, we've reached 0, and then it is going into a positive value, reducing back and again coming 0, then going to a negative value, and then coming back to again 0. Now, this thyristor, which is used in those particular converters and inverters, okay, remember we are calling conversion means converting it from AC to DC, and then inverting it from DC to AC, or if you're going to have from AC to AC directly. So whether it is a synchro converter or a cyclo converter, we are using always the AC element over there. Okay, we are not using a DC element to forward bias this thyristor. Therefore, from every instant, you're going from 0 to a positive, coming back to 0. So at the 0 crossover points, your thyristor should stop conducting. Okay, so when it is going positive, okay, it should conduct. So you're going to have plus and minus. And when it comes to 0, this should go, isn't it? On the contrary, what happens? Yes, the voltage is removed, but there is a very, very small current that is going to be passing over here. Okay, so this is your voltage curve. Okay, your current should have been 0, but your current is lagging a wee bit. Okay, so when the voltage is gone 0, your current has not yet gone to 0. It goes to 0 at this particular point and then keeps on like that, like that. Okay, and instead of coming to 0 over here, okay, I'm just showing it exaggerated. It's very, very small. So instead of being at 0 over here, it is not yet gone to 0 point. It is still there. At 0, when the voltage is gone to 0, there is still a little bit of current flowing. Very few microamps, very, very small current. So your thyristor is basically still conducting, no matter how little a current, it is still conducting despite this positive and negative being removed. Okay, so having seen that the current is still conducting through this, despite your voltage reaching zeros at these particular points, this is called the internal circulating current. Okay, everybody's clear with the internal circulating current or circulating internal current of a cycloconverter? Yes? Any queries or doubts? Right. So keep this in mind. This circulating internal current or internal circulating current of a converter, whether it is cyclo or your synchro converter. As I said, this current is still conducting no matter how small, despite your voltage reaching 0. Okay, so I'm drawing the graph over here. Okay, so this is your voltage and this is your current. Okay, it's a very, very slight your current. Okay, so voltage is in purple, current is in red. That is this particular sinusoidal curve. What type of circuit is this? Where your current is lagging your voltage. What type of a circuit is it? Anybody? 12 people are online.
Inductive, sir.
Yes, it's an inductive circuit. Okay, so this particular thing becomes an inductive circuit because your current is lagging the voltage no matter by how much of current is flowing. Even a small flow of current flowing, when your voltage becomes 0, makes it an inductive circuit. Okay, so please bear this in mind because we are going to tackle something else in the next chapter, which is your shaft generator. Okay, so everybody's understood what is the internal circulating current? It is the current that still keeps flowing, though very, very small. When your voltage has become 0, in other words, your voltage, biasing voltage across the thyristor has turned to 0, where the thyristor should have normally stopped conducting, there is still a very small current. You can call it a leakage current if you want to call it that. Okay, then that thing is called as the circulating internal current of a cycloconverter or even a synchro converter, because we are using these very same thyristors. Okay, right. So having seen that, okay, see, this is that answer. There is a fraction of time lag where the current is still flowing through the thyristor before it is switched off, while voltage in the current has already fallen to voltage in the circuit has already fallen to 0. Okay, right. So now we will move to the other part, which is your I have not opened it out. Give me a moment. Which is your shaft generator. Okay. Right. Oh, sorry. Okay, so this is your shaft generator. And I request you to retain in mind what I mentioned about the internal circulating current of a cycloconverter or synchro converter. It is that little current that is still flowing despite the voltage, biasing voltage of your thyristor being already at 0. Okay. Now coming to the shaft generator. Shaft generator, you need, for that matter, any generator, you need a prime mover. And here, in this case, the prime mover is none other than your main diesel electric engine. That is acting as the prime mover. Okay, so here is the block diagram of it. And generally, if it is ever asked in your orals about the shaft generator, then they ask you to draw and explain. Okay, never mind the writtens, but in the orals also, they ask you to draw and explain the shaft generator and how it works. Right? So we have your main engine acting as the prime mover, right? And when this is going to be acting as a prime mover, what is your RPM of your main engine? I don't think it is anything greater than, it is always less than 150 RPM. Okay, unless you are on a man of war, that is your normal naval vessels, but we are not on those type of vessels. We are on a normal cargo vessel. So I don't think there is any main engine that is going at 100, even at 150. I do not know. I worked on a ship that was giving me 125 RPM. Okay, so it depends. You might be having a high-speed diesel engine, but most of the engines that are fitted on board of big cargo vessels are slow-speed diesel electric engines. They are not medium or fast-speed. Those are installed on your naval vessels. Okay. Okay, let's assume 150 RPM. Okay, but it's generally less than that. And you're having your alternator for your normal generator, a brushless alternator. Now, if you have seen your brushless alternator, that shaft is turning at around 800 to 900 RPM. Okay, 800 to 900 RPM. What is this? I said less than 150 RPM. Let's take it as 150 RPM. Where is 150 RPM? Where is 800 to 900 RPM? So therefore, if you're going to have this voltage, you're not going to develop enough voltage over here to be output to the main switchboard. Therefore, you have something called as the power take off, PTO, also called as the coupler. Basically, what is the coupler? It is a gearing ratio. A gearing ratio that will make this 150 RPM equal to 800 to 900 RPM, whatever the RPM that is there for the manufacturer, so that you develop the exact particular voltage. Okay, so assuming that whatever is the ratio of those gears, this is turning up to give you this particular RPM. And we have seen how voltage is generated by a brushless generator. I'm not taking that topic, but everybody knows that due to residual magnetism, a small voltage is built up in the exciter coils. Okay, and then as the rotor picks up speed, more and more voltage is current is given through your rotor coil, which develops more and more electromagnetic lines of force, which in turn cuts your stator coils, and that's how voltage is induced into your stator. And then you have the AVR coming in the circuit. As the voltage is low, AVR will be giving more to its excitation, okay, exciting coil, and then that's how your voltage comes up to 440 volts. So that was in brief, right? So that is what is happening, and here you get three-phase 440 volts AC, okay? Then it comes into this thing called the frequency converter. At one glance, of course, the full circuit is not given, but just giving you a glance of this. Of course, this is instead of diode, it is also a thyristor. Okay, so it is a thyristor. So one glance should tell you what type of frequency converter. Okay, what type of converter is it? Is it a cyclo converter or is it a synchro converter?
Synchro.
Right? Yes, it is a synchro converter. Why? Is because we are converting three-phase. Of course, this is just one block. We're not showing all the thyristors. This is converting three-phase AC into pulsating DC over here. Okay. Then, of course, you're having the smoothing out elements. The capacitor is not shown. And you have a smooth DC waveform over here. Then this DC is inverted back into three-phase 440 volts of AC. Okay. And through your ACB, it is then switched on to the shift load. Now notice this thing called as minus Q. What is this minus Q representing?
Reactive power.
Sorry, your voice is garbled.
Reactive power.
Reactive.
Yes, correct. Reactive power. Okay. If you're going to have that reactive power, okay, very quickly, very quickly, a recap of the power triangle. Okay. So this is your power triangle. This is your real power, kW. This is your kVAR, reactive power or wasted power. And this is your kVA, apparent power. So if this is going to increase, in other words, your theta is going to increase. In other words, your power factor is going to decrease. Okay. So this is very correctly, as you all said, reactive power. And this reactive power is because your ship's load is inductive in nature. Okay. Your ship's load is inductive in nature. Why? Is because we are having so many motors, we are having so many heating coils. So a lot of coils are there in that circuit, making it basically a inductive load. Now coming back to this converter, and when we talked about that circulating internal current of a cyclo converter, as I said, even for your synchro converter, since we are using thyristors, we said that circulating internal current is due to the leakage current whilst your voltage is already zero. Current, no matter how small it is still flowing, making that circuit a inductive circuit. So this circuit that you are using here is also an inductive circuit purely because of that circulating internal current. So your ship's load is already inductive nature. Now you are adding yet another minus Q, making this minus Q even larger. In other words, your power factor is going to reduce, your efficiency of the system is going to reduce, and you are going to be consuming more fuel rather than producing proper power. A very detrimental thing. Okay. So we have to compensate for this. We will see how we are going to compensate for this minus Q due to that circulating internal current of these thyristors that are used in this particular frequency converter circuit. Okay, we'll see that later. But now we're talking about generator. In other words, we have to see how we can control the voltage, how we can control the frequency, just like any other generator. And in addition to that, how we can control this minus Q. First, the voltage. You're having your voltage and frequency feedback from your MSB. Your voltage feedback is again given to this circuit, which consists of an AVR. So we know how an AVR works. When the voltage increases, it will act to reduce. Okay, here's the excitation thing for reducing that voltage or increasing the voltage by inducing it into the exciter cycle. Okay, and we know how a brushless generator works. So in a very similar manner, your voltage, if it increases beyond 440 volts, is reduced back to 440. And if it reduces below 440 volts, it is increased back to 440. Okay, so we know how the voltage is done. How is the frequency controlled? If you remember when we talked about frequency control with regard to the maneuvering of the ship, because we are using those converters, both synchro and cyclo converters, for electrical propulsion. And therefore, we had that speed is equal, or speed here in the case N, speed is equal to 120 multiplied by F divided by the number of poles. Poles are fixed. This is fixed. So what you can change, you can either increase the frequency or decrease the frequency, whereby you increase the speed or decrease the speed accordingly. So everything, the speed here depends on the frequency. Okay, and if you remember, I said, how is the frequency controlled? The frequency is controlled as to how fast you fire these thyristors. Faster you fire them, greater is the frequency. Slower you fire these thyristors, lower is going to be the frequency. And therefore, we saw how we could control the speed of the ship. But in the same manner, this frequency over here is being adjusted constantly due to the feedback one is getting, and then the firing control circuit takes over and fires these thyristors accordingly. Okay, so your frequency that is going to be on this particular thing will be kept as close to 60 hertz as possible. Okay, so we've seen how we control the voltage. We've seen how we control the frequency by the firing of these thyristors. Now we have to take care of this. Okay, the kVAR. We don't want this minus Q to be added to make the ship's load even more inductive in nature. So therefore, you are having a kVAR feedback from your main switchboard to this very same circuit that is already controlling voltage and frequency. It is also giving you an excitation for your kVAR control. And this excitation is to your synchronous compensator. The synchronous compensator is nothing but a synchronous motor. Okay, just running by itself. It is not connected to any load, such as we saw that synchronous motor in your this thing, and we'll see two videos also shortly after I complete this topic. Okay, on the ASI pod, which is driving your particular vessels, merchant navy vessels, even sometimes your passenger vessels. Okay, so if you have seen, if somebody has taken the topic of motors and has done synchronous motors with you, a synchronous motor requires its rotor to be supplied voltage. This is that rotor winding. Okay, if the synchronous motor is overexcited, that means you're overexciting it by this particular voltage, then your particular minus Q is taken care of, is because you're adding a plus Q. If you don't need that excitation, so it is going to be normally excited, so it will be neither plus nor minus Q. And if you want it to be more inductive nature, then you're going to give it a minus Q. So it will be under excited, either overexcited, normally excited, okay, or under excitation, which if it is overexcited is basically when you're going to overexcite, that means you're going to have your current leading the voltage. In other words, it's going to become a capacitive circuit. That is why it is called a synchronous compensator, where this motor is going to behave like a capacitive circuit. Instead of this, you could have had a bank of capacitors, like we saw when we were doing the static AVR. Okay, you could have that also. Okay, so this synchronous compensator, which is nothing but a synchronous motor, is going to give us this plus Q, as you can see over here, and that is going to be switched on to the main switchboard. So depending on what is the feedback of your minus Q, this one is going to give you that much of excitation extra to compensate with a plus Q, and that's how this particular minus Q is negated. Your KVR is reduced, your efficiency, your power factor is increasing, and your overall efficiency of this particular generator has also increased. Okay, everybody clear? Right, we'll see the advantages and disadvantages of your shaft generator. And then we'll see those two videos related to the converters, okay, used as electrical propulsion. Okay, so what are the advantages of your shaft generator system? Biggest advantage, no extra air pollution. You're not using an extra generator. Yes, these days we are having a scrubber, I believe, retrofitted. In my time, that was still under discussion. Okay, those that don't have it will have to always, whenever they're going into the Sikka areas and all, will have to use special fuel. Okay, both for your main engines as well as for your diesel engines. Okay. Why is because NOx and SOx are there. So if you're not using an extra diesel generator, then only your main engine is polluting. Okay, if that is, you don't have a scrubber. I think now, I don't know when it is going to become mandatory, but sometime in the very near future, it's going to become mandatory. But many ships have already started retrofitting a scrubber so that whatever the exhaust that is coming from the main engine and your generators is cleaned, and all that you get out is only hydrogen and water. Okay, so two non-polluting elements, clearing this NOx and SOx. So one of the big advantages is already your main engine is covered by that. Okay, so no extra NOx and SOx are being there to pollute your atmosphere. Low noise level. You shut down, suppose 2 generators or 3 generators are running, you just shut down one of those generators and there is a marked improvement in the noise level. Okay, so naturally, whenever there is no generator running and only your main engine is turning to produce voltage by the shaft generator, it's the noise of only the main engine. So those other generators are at standstill and therefore your noise is reduced. Number 3, it is more cost effective as it does not require extra expensive fuel for power generating, as your main engine is the prime mover itself. This is contradicted by a remark in the disadvantage, and we will see what it is. Yes, you do consume extra. Okay, so let's say your main engine, of course, this is a big vessel because I've been mostly on big vessels, say VLCC, say is consuming 40 tons per day. Okay, 40 tons per day. If you are not having a shaft generator, then out at sea, only one generator is consuming. So your generator is consuming roughly 2 tons per day. Okay, so total will be what? Total will be 42 metric tons of fuel. Okay, if you are using a shaft generator, because an extra load is coming on the main engine, then your main engine instead of 40 tons is consuming 41 metric tons. Your generator is not consuming anything because all your generators are off. So this is nil. So what are we consuming totally? 41 tons. So that is 1 ton saving. Okay, 1 ton saving. I do not know what is the cost of your fuel oil today, but at the time when I retired, it was about 750 to 800 dollars to a metric ton of fuel oil. Okay, so given the today's scenario, I'm not sure, but it should be around the same, if not more. So you can see if you're saving 1 metric ton per day, how much your owner is saving. Okay, so yes, we are not consuming that much of fuel, but certainly yes, we are consuming extra fuel by the main engine by just 1 metric ton extra, whilst you're not consuming any extra fuel as far as your generators are concerned. Number 4, the wear and tear and hence maintenance schedules and costs for the same reduces for other independent driven generators. Now, since the other generators are not running, most of the time your shaft generator is running. Okay, so the maintenance of your other generators comes down because all the maintenance on the other generators, I'm not talking about the alternate, I'm talking about the generator engines. The third engineer or fourth engineer, whoever's in charge of that, he'll be a very happy person because that particular schedule, which is scheduled after so many running hours, will definitely not come in his contract, maybe not even in his reliever's contract. Okay, so the number of running hours, the maintenance schedule is done on the number of running hours of a generator, and therefore, since those running hours are very, very less, everything gets postponed. And even so, when you're going to postpone an expense, that means you are saving a bit of money. Instead of spending $1,000 today, you are spending $1,000, say 3 or 4 years later. That's a huge saving. That $1,000 can earn you a lot of interest in the bank. Okay, so that is what it is over here. Okay, number 5, occupies less space as it is installed close to or in line with the shaft of the main engine. Not think whatever space is vacated on your generator engine platform. Okay, that is going to be occupying the same space down there. It's not that small. Okay, it's quite a big attachment to your main engine, and it's occupying quite a bit of space on your bottom plane. And number 6, low spare parts cost and maintenance is easier. Okay, that is coupled with your number 4. Okay, so both these are interrelated. What maintenance the engineers only have to do as far as your shaft generator is concerned, that coupling, that PTO that I spoke about, that is the main thing, and the thing for coupling to that gear. Okay, that is all the maintenance that they have to do. Whereas you as an electrical officer will have to do the routine alternator maintenance as you would do for the other alternators. Okay. So those are the advantages of your shaft generator. For the advantages, you also have disadvantages. And the main disadvantage is that your main engine is pushing your ship through the high seas. You might run into some heavy weather, okay, where you're getting headwinds, you're getting head swell. Okay, the ship is pitching and rolling. Okay, in other words, your RPM also will never ever be steady. It can fluctuate up to 150, might even come down by 20 RPM. Of course, if it goes below a certain set value, then you'll have the main engine tripping. Okay, so with so much of RPM fluctuation, remember that when you're going to have RPM changing around, then the field that is going to be cutting your stator field from your rotor coil, that is also going to reduce, isn't it? And therefore, your output voltage will keep varying from reducing to increasing, reducing, increasing, increasing, reducing. So it's a continuous process whereby the AVR for that has to be in continuous operation in order to keep the voltage as constant as possible. Likewise with the frequency. If the speed falls, remember the frequency also falls and vice versa. Okay, so the frequency, the firing also has to be taken care of. Okay, so there will be an input to that thing saying that, okay, now my speed is fallen, please fire it faster. so that my frequency comes back to 60 hertz. And if the speed of the shaft is increased, obviously it will be a command to those thyristors. Now it's gone beyond 60. Please fire those thyristors slower so that I get the correct frequency. So continuous changes with regard to voltage and frequency. Number two, no power generation in port as ME is in stop condition or in maneuvering. You cannot maneuver and generate power from your shaft generator, mainly because of the speed. Unless you have a CPP, controlled pitch propeller. Okay, in this type of system, your main engine is turning at its normal RPM. Only thing is your propeller blades are turned in such a way that you have neither thrust nor anything to make the ship go in the aft direction. Okay, so your ship is at standstill even though your main engine is turning at full RPM, all by changing the pitch of your propeller. Okay, so unless you're having that, if you're having a normal propeller, then you cannot generate using this particular shaft generator. Okay, number three, due to additional attachment to the main engine, the shaft of the main engine, load on the engine also increases, resulting in increase in specific fuel as well as cylinder oil. Don't forget your cylinder oil is also consumed. Okay. Extra load on the engine, then the lubrication is more. Okay, your alpha lubricator and all that, they will sense that, and depending on the load, lubrication for the main engine units will be more. So you're consuming, including extra fuel because of the load on the main engine. You're also consuming extra main engine lube oil. Okay, because again of the extra load due to the shaft generator. Number five, it requires, number four, cannot cope up alone when the load demand is high, as it may affect the main engine performance and maintenance. That even for your normal generators, if the load increases, then you always start another generator. You don't like to put, even though the generator maybe, it says it can run at 100% load. No chief engineer in his right sense is going to run his generators at 100% load. He will run it normally at 80–85%. He'll never take it upward again. Okay, so if you're going to put an extra load on your main engine, then your main engine can run into trouble. And that's the main thing that is going to put your ship all over the world and earn money for the owner, and in turn earning money for the owners, earning money for you and me. Okay, so nobody wants to screw around with the main engine. So therefore, if an extra load is coming on that, in other words, you need extra load, then you always have to start up a secondary generator. Okay, another normal generator. Number five, it requires gears and couplings and other complicated arrangements for its installation. So I told you that PTO is there, and then how to couple and decouple the shaft generator from the shaft of the main engine. Okay. So these are the advantages and disadvantages of your shaft generator. The shaft generator, why is it being taken out? It's because we are using a frequency converter. Okay, where AC is converted to DC and then back into AC. Okay, everybody clear? Any queries or doubts? Okay, so let us see those two videos with regard to the synchronous motor that your converters are going to be driving. Okay, in other words, for electrical propulsion. This motor is nothing but your azimuth motor. Azimuth means turning around the y-axis 360 degrees. Okay, so if this is the y-axis, okay, if this is the y-axis, then it can turn full 360 degrees in either way. Okay? Either way, it can turn. Okay? So that is your azimuth motor, and we will see both these. One is a smaller yacht, or also a passenger vessel, but a much smaller one, and one is a really big one. Okay, so we'll see both those videos. Okay. Sorry, not this one. Give me a moment.
Scenic's first
Okay, so this is that azipod in which your induction motor is inside here. So you can see that this is going to be your converter circuit. It's huge, not like the converter or inverter that we have at home. Of course, that video that I showed you about the inverter was the one that we use normally at home. Okay, excepting that here it is on a much, much larger scale. Okay, and that inverter or converter is going to be driving the motor inside this, which is a synchronous motor. So not only is it going to be acting as a thrust to your vessel, also as you will see from inside the video that this is shaped like a rudder. So you don't have a separate steering gear thing for this. This one acts as a thrust as well as for directing your ship in whichever direction you want to go. Okay, so we'll see that.
Scenic's first discovery yacht, Scenic Eclipse, will feature the latest version of the advanced Azipod propulsion system, Azipod D, which won a prestigious Marine Engineering Award in 2015. Azipods are unique in that they position the electric motor directly next to the propeller, which eliminates the gear and drive shaft noise and vibration associated with other propulsion systems. Guest comfort is always a high priority, and Azipods have the lowest noise and vibration levels of any large ship propulsion system, which also offers minimal disturbance to marine life. Azipods are also friendly to the wider environment, being up to 12% more fuel efficient than standard systems, and also allow slightly increased speed for installed power output. Working in conjunction with our state-of-the-art GPS dynamic positioning, they keep the ship stationary without the use of anchors. However, Azipods really come into their own in the challenging polar regions, and is one of the reasons why Scenic Eclipse will have the highest passenger ship polar classification, PC6, Ice Class 1A Super, allowing a wider safety margin and sphere of operations in Arctic and Antarctic regions. This system enables a ship to break ice using a revolutionary principle that greatly improves the maneuverability of ice-going vessels. The rotating unit allows the propeller thrust and wake to be directed against the ice, working in reverse to clear a channel for the ship. It can even break through an ice ridge. There's no need for icebreaker assistance, thanks to the safe and efficient operation capabilities of the Azipod. All these innovative features allow Scenic Eclipse to do what it does best: provide her guests with the ultimate luxury cruise experience, no matter what the outside weather conditions. Scenic Eclipse, the world's first discovery yacht.
Okay, so this is one video, and now you'll see it on one of the bigger passenger vessels. Okay, we won't see the entire video over here, only the relevant parts.
two azipods that we have now. In the Freedom, we have two azipods that are the maneuverable ones, the ones that we can rotate 360 degrees. And then we have one fixie-pod, which is fixed in its position, and it pushes. But the azipods are actually pulling. The propellers are in the front.
Okay, so in the case of this particular vessel, these azipods, instead of being located behind of the vessel, after the vessel, they are located forward of the vessel. So as the captain has mentioned, they are going to be acting like propellers of a plane, pulling the ship forward. Okay, rather than providing thrust, it is pulling the ship forward, and then you're having one stationary one from behind. So you're getting both pulling forward and pushing, a push-pull sort of. Okay.
Very much like you'd have on an airplane. And the advantage of that is that the propellers then are working in a much more pure environment. The water flow that's hitting the propellers is much more laminated than the case of a propeller that is working at the end of a shaft. So vibrations is not a problem at all with the azipods.
And now for some cargo vessels also. Going north of Russia, because the ice is thin, now more and more ships are using that route without an ice bridge. And you can see that they have to move up, not in the normal forward condition.
The ability to direct the thrust exactly where we need it, the ability to do a crash stop, for example, keeping the propellers rotating the way that they are, and simply reversing the direction of the propeller 180 degrees is a huge advantage. So certainly azipods have made a significant contribution to the overall safety levels that we're able to operate under. With the azipod, I can rotate the entire propeller and direct the forces exactly where I need them. And that's what makes the azipod such a wonderful tool for the ship handler.
Okay, so this was of 2006. Today we are 2023. There will be many more vessels. Okay. This was long back, more than 15 years ago. Okay. Right. So two very interesting videos which were related to the azipod that was using the synchronous motor. And for the synchronous motor to work, we were using either a synchro converter or cyclo converter. Nowadays, they are preferring the cyclo converter for the simple reason that you are not going to have any extra components in the form of, converting from AC to DC and then back into AC. You are going to convert directly AC into AC. Okay. Right. So that was the topic on converters. And as a offshoot for the converters, because we were using one of those converters in your shaft generator, the shaft generator. Okay. Any queries or doubts on any of those topics that we covered in those chapters before we move forward to this particular one? Portable gas detection equipment. Okay, so this topic, portable gas detection equipment, we'll be seeing the explosimeter, the tank scope, the multi-gas detector, then standalone O2 detector in the form of your O2 analyzer. Those who have been on tankers will know what I'm talking about. For those who have been on bulk carriers and container vessels, that will be only a point of interest, because basically, if questions are going to be asked to you, they ask you on which ship you are working on. So if you're a container vessel guy, then they are not going to ask you everything with regard to tankers. That would be silly on the part of the surveyor. Not to say that he is not allowed to, he can very well ask, because there are certain electrical and things that you need to know and you have to know. But things like your O2 analyzer, since that is used only on tankers, it's definitely not going to be asked to you if you are a bulk carrier guy or a container vessel guy. But let us see all these things. So we saw the O2 analyzer, plus apart from the multi-gas detector, which is there on board all ships, let it be tankers, let it be let it be your container vessel, let it be your bulk carriers, you will be carrying a multi-gas detector. That is 100% certain. Because on containers, you are going to be carrying certain containers that are having dangerous cargo. Whatever that dangerous cargo is, might be emitting some fumes, flammable gas. Okay, we had one instance, I think it was in 2021 or early 22, when one container vessel caught fire due to some chemical dangerous gas cargo that we were carrying in containers, and then it was a total loss and she sank off the port of Colombo. Okay, we have a very pertinent example there. Bulk carriers, when you carry coal, coal emits methane. Methane is a very combustible gas. Okay, so you need to determine what is that combustible gas, what is the quantity of that combustible gas, because when they come together in the right format, the triangle, the fire triangle, sufficient fuel, sufficient oxygen, all you require is an ignition source and you will have a fire and explosion. Okay, so in order to avoid this fire and explosion, we have all done, irrespective of whether you're joining a container vessel, bulk carrier or tankers, we would have done the firefighting course, whether advanced or basic. This particular diagram would have definitely been explained to you. Not the way I'm going to explain to you, but in a very basic format, they would have explained to you. Okay, what I'm going to explain to you here, please pay very specific attention, because guys, they can cross-question you so much on this, and this being a safety-related topic, if you do not answer correctly, unfortunately, if you are going to answer all your technical questions correctly and do not know anything about this type of a diagram called the flammability diagram, they can fail you. Okay, so do pay specific attention with regard to this. Now, what I want to draw your attention to right now is this diagram that I have personally drawn is a wee bit off as compared to this diagram. Okay, so I will be referring to both diagrams. One of the things that you will notice is that from point F, I've taken it vertically down towards your x-axis. It shouldn't have been the case. It should have been at a slanting line. Okay, a slanting line should have been that particular thing. Okay, second thing is this line AB, I've drawn two slanting towards the left. Okay, it should not be the case. In this case, it should have been more straighter as shown in this particular diagram. Okay, so these are the only two discrepancies as far as as far as this flammability diagram that I have drawn. Okay. So in the orals, they will ask you what is the flammability diagram and draw and explain. Okay. What is the meaning of flammability diagram? So what is the flammability diagram? The flammability diagram is a document. Okay, it is an important document, an important safety document. You can add the word safety, used across the world. In other words, worldwide, irrespective whether whatever your flag is, whichever country you go to, North Pole, South Pole, it is going to be there. Worldwide, in order to understand, and bottom line is to prevent a fire and explosion. Okay, this is the bottom line. We want to, at any cost, prevent a fire and explosion on board our ships, because that could lead to some very disastrous consequences, even the loss of life as well as the loss of the ship itself. Okay, so it is used, it's an important document, an important safety document that is used across the world or worldwide in order to prevent fire and explosion. Okay, generally used on tankers, but as I said, you can also have it on board your particular bulk carriers, because your bulk carriers are carrying this thing also, coal. Okay, and you are going, that coal is going to emit methane. Methane is a flammable gas, so it can come in useful there as well. Okay. Further, so your definition of your flammability diagram does not end there. Further, it explains to us how a gas, what gas? You can say a flammable gas or a mixture of two gases will behave and catch fire with the dilution of another gas or air. So air has to be there in order for anything to burn. What is this other gas that they are talking about? This will be pertaining to only those on board tankers, and everybody knows that other gas that you are talking about is none other than your IG, inert gas. Okay. So this is your definition of your flammability diagram. It is an important safety document used worldwide in order to prevent a fire and explosion. It also tells us how a certain flammable gas with a mixture of another gas together with air, okay, will cause a fire despite having your IG, okay, the third gas. Okay, so let's see what that is all about, and I'll be sometimes referring to this diagram wherever required, but mostly I'll be referring to this diagram. Okay, all that you have to remember is this line that I've drawn from F to I should have been actually slightly slanting towards the y-axis, and this line which I've drawn slanting too much towards the y-axis, it should have been more vertical in nature. Okay, that's all. Right, so starting with this particular diagram, as you can see that the x-axis is demarcated with oxygen in a percentage value. Okay, so you have 0% right up to 20.9. Okay, round it off to 21% of O2. On your y-axis is given in your hydrocarbon gas, that is the flammable gas, in a percentage volume. Okay, a percentage volume. Okay, now we are going to see all the other things which are related to this particular flammability diagram. This slanting line, okay, remember, as I said in the orals, it is asked, draw and explain the flammability diagram, and you've drawn the x-axis and the y-axis. You mark the y-axis accordingly, you mark the x-axis accordingly, and the very next thing you're going to do is draw this slanting line. Okay, as I said, that slanting line is going to be more or less like this. Okay, So you're going to draw this slanting line and the examiner will stop you and say, what does this slanting line mean? Guys, I'm pretty certain anybody who has gone for your advanced firefighting, forget about basic firefighting. Basic firefighting is very basic. Even the so-called advanced firefighting course, nobody has explained what this line is. All that they would have done in that firefighting course, X axis, Y axis, drawn this line, drawn this curve, colored this curve over here, flammability range. Don't go between this, because if you go into this thing, you will have a fire and explosion. Khatam. Okay? Nobody has explained what the hell is this line? How you got this curve? Yes, they would have told too lean an atmosphere, too rich an atmosphere. What is LEL? What is HEL? Yes, they would have told you that. Because if they didn't tell you that, then that is not a proper firefighting course that you have attended. Okay, so here in the examination, every single thing becomes important. This line included, okay? As I said, this line included. This line AB, if the examiner asks you, what is this line AB that you have drawn? Refer to the box on the right-hand side. Line AB represents the mixture of that flammable gas, the hydrocarbon gas. Now we are relating mostly to onboard tankers, okay? So that is why we are relating to hydrocarbon gas, because we are carrying fuels. And fuels emit this hydrocarbon gas, methane, pentane, butane, so on and so forth, all highly flammable gases. So instead of putting hydrocarbon gas, you can say flammable gas as well as O2. Remember, without O2, nothing can burn. Okay, heat, fuel, and O2. Sufficient amount of O2. If this was absent, okay, you are definitely not going to have fire and explosion. You require all the three sides of the triangle to have a fire and explosion. Okay, so mixture of that particular flammable gas as well as O2 is represented by this line AB. More correctly, as I said, it is more vertical than the slanting line that I drew in this particular one. Okay, so line AB is the flammable gas plus O2. Okay, and why am I saying this line is a little bit wrong? It's more thing, because if you're going to draw a line down to the x-axis from point B, you will see it is about, this is 20.9, approximately 21% of O2. Okay, if you're going to draw a line, straight line down, okay, to your x-axis, it's not a very straight line that I'm drawing, but you can understand what I mean. Instead of 20.9, this might be 20%. 20% is very close to 21%, isn't it? So definitely a good supply of oxygen, enough to cause a fire and explosion. Okay, right. So that is what is your line AB. Anything to the left of this line AB contains that third gas that we saw in this particular definition. Okay, the diagram explains to us how a flammable gas or a mixture of two gases will behave and catch fire with the dilution of an other gas. That other gas is Ig. Okay, so anything to the left of this line AB, that means going in this direction, okay, has that extra gas called that Ig, or inert gas, right? So that is your line AB. What is this line AC or CA and line BD or DB? Line AC represents more air than your flammable gas. And when you're talking about more air than your flammable gas, remember I said for the triangle to come together, you have to have sufficient amount of air of O2. You have to have sufficient amount of the fuel. You have to have a sufficient amount of heat. When they all come together in the right proportion, you are having a fire and explosion. Now, in this case, below this point C, we are in a place where we are having so much of air, little or no hydrocarbon gas. It is like taking, let's say tomorrow prices of petrol are going to go up. Everybody is rushing to the petrol pump and buying petrol in cans and bringing it home. Okay, normally you're not supposed to do that, but okay, let's take this as an example. You brought it home and you find, Are Bapre, I don't have any duckans to cover these cans. So all the cans are lying open there. Of course, it's going to be a loss for you because that petrol is going to evaporate. The thing that is going to evaporate means that there are going to be fumes, that flammable fumes, the flammable gas. Remember, it is the fumes or the gas that burns and not the liquid itself. Okay, so let's say you are taken and kept in the room where you are hearing my lecture. The room is 10 by 10 or 12 by 12. Your fan is on, you're listening to my lecture. Nothing is happening to you, is it? Still there are flammable fumes. Suddenly you feel a urge to have a cigarette, you light a cigarette, still nothing happens to you. Why? There is so much of oxygen, so much of air, that it is swamping those particular flammable fumes. Little or no flammable fumes, plentiful of air. In other words, this side of the triangle you are missing out on. So if this is heat, this is O2, and this is fuel, then you are going to be, when you're talking about this line CA, you have taken out this part of the equation. No matter how much of heat, no matter how much of O2 is going to be there, you are not going to have a fire explosion. Such an atmosphere as colored here in green, which is represented by this line CA or AC, is called too lean a mixture. Okay, so this is too lean a mixture. Opposite to too lean a mixture, the line BD is having too rich an atmosphere or too rich a mixture. Now, as I said, it is opposite to too lean a mixture. In other words, you are going to have so much of fuel, but little or no O2. And when we are having one side of the triangle missing, no matter how much of heat you're going to give, you're not going to have a fire explosion. So here you're having so much of those fumes, so much of that particular fumes of that particular fuel, that it is going to be bereft of any O2. And remember, for any burning process to take place on Mother Earth is O2. Without O2, you cannot have any burn. Okay? So this makes this atmosphere too rich. Rich in what? Rich in the fumes, rich in the fuel that we are talking about, that flammable gas that we are talking. Okay? So such an atmosphere is called too rich an atmosphere. And that is represented by line BD, which is lying on this line AB. Okay, so we've seen what is line AB, we've seen what is line AC, we've seen what is line DB. We will come to these other dashed lines a little later. Okay. Now, let's understand how we get this flammable range. Okay. This flammable range is not reason. It is flammable region, flammable range, flammable curve, whatever you want to call it. It is this curve that is going to be putting you and the entire ship in danger. So we have to avoid this curve at all costs. But how did we get this curve? That again was not described, not explained in any of the advanced firefighting courses that you all might have attended as part of your mandatory STCW courses, right? Let's go over here because then I will be able to explain it. That is why I said I'll be moving from my diagram and this diagram because you can see certain things are missing here. Okay. Now, on this line AB, we had marked the points D and C. Okay, and we have discussed already what is CA and what is DB or BD. Now let's talk about point D itself. Let's talk about point C itself. Point C on the line AB is the lowest concentration of the hydrocarbon gas or the flammable gas. Let's not call it hydrocarbon gas. It can be any gas. As long as that gas is flammable, that is going to be represented by point C, and that is going to be the lowest concentration of that particular flammable gas. Together with air, remember on this line AB, we are having sufficient of O2. So point C, again, if you're going to draw it down to the x-axis, you're going to see how close it is to 21% of O2. So you're having sufficient of O2, sufficient of that fuel, okay? So all that you require is a heat source, an ignition source, and then you will have a fire and explosion. Point C being the lowest concentration of gas is called the LEL, lower explosive limit, lower flammable limit. Okay, both mean one and the same thing. It is the lowest concentration of that flammable gas or vapor in air that is capable of causing a fire or explosion in the presence of an ignition source. Below that point C, and we represented that as line AC or CA, becomes too lean an atmosphere. Okay, so that is LEL, LFL. LFL standing for lower flammable limit. LEL, lower explosive limit, both mean one and the same thing. Opposite to point C, we have point D. Okay? And if this is the lowest concentration of that flammable gas, point D will be the highest concentration of that flammable gas, which will have sufficient of O2 since we are still on this line AB. And remember, line AB is that flammable gas plus O2. Okay, so there is sufficient amount of O2. Of course, now when the line is going to be so slanting, it's going to come quite far away from 21%. So now, if you're going to draw D, and that's why I'm saying looking at this line, it should have been more straighter in my diagram. You will see that it is still very close to 21% over here. Okay, so that means you're going to have enough of O2. You have the highest concentration of this gas. All that you require once again is this ignition source, and you will have a fire and explosion. So HEL, HFL, HEL higher explosive limit is the highest concentration of that flammable gas or vapor in air that is capable of causing an explosion of fire with the presence of an ignition source. Okay, anything above that becomes too rich an atmosphere, and no matter, even if you're going to provide an ignition source, you're not going to have a fire and explosion. HFL, same as HEL, higher flammable limit. Sometimes it is replaced by upper flammable limit or upper explosive limit. UFL, UEL, all mean one and the same. Okay, everybody clear thus far? All these various parts of your flammability curve. What is this line AB? What is BD? What is line CA? What is point C? What is point D? Okay. Point C, by the way, is taken as normally 2%, but for the examination purposes, please remember it as 1%. Okay, so by taking it as 1%, we are being more on the safe side rather than taking as 2%. Now this LEL value will differ from flammable gas to flammable gas. We are not taking this as a general rule. For hydrogen, the LEL is going to be 4%. We'll see in one of the videos also. Okay, it can be 4%. Okay, so we will not be, think this is a general outlook that we are taking it as 1%, because if you are taking it as 1%, then you are being more on the safe side. Okay, right. So we've seen that much. Does anybody have any doubts or questions with regard to whatever I've explained thus far? Please do ask now, because then we can go ahead.
So can you explain?
Explain what?
So slanting line.
Okay, the slanting line AB. Okay, slanting line AB, as I said, should be more like this, more vertical than so slanting like what I've drawn. So this is incorrect. It should be more vertical. Okay, so never mind. We know that already, and I'll be posting both the things to the app, so you can again go through it. Line AB consists of the flammable gas plus O2. Okay, so anywhere on this line, and let me now go to this one, anywhere on this line, you're going to have that flammable gas. Anywhere on this line, you are going to have a sufficient amount of O2. Okay, but where on this line you're going to be? If you're going to be on the line AB at this particular point below C, then you are coming into this particular thing called too lean an atmosphere. You are not going to have a fire and explosion, even if there's a presence of an ignition source. If you're going to be on this line AB above point D, then again you're not going to have fire and explosion because of this atmosphere being too rich. Anywhere between point D and C, both inclusive, you will definitely have a fire and explosion if you're going to bring an ignition source. Okay, so clear with what is line AB?
Yes, sir.
Anybody else? Any further doubts or questions you want to be cleared before we move forward? Okay. Now you would have seen from point B, I'm now going to refer my diagram rather than this, because as I said, certain things are missing here. Okay, with more technical things, I will be referring to this. Otherwise, I'll be referring to my diagram. Okay, you can see from point D, I've extended a dashed dark blue line towards the y-axis, but I've crossed the y-axis and I've labeled it as 10% HEL or HFL. You are going to go into the higher flammable or higher explosive limit at point D. Okay, up till here, you are in the lower flammable limit. From right down here up till point D, you are at the lower flammable limit. Above this thing, you're going into the higher flammable limit, and point D is 10% of that higher flammable limit or higher explosive limit. Okay. Similarly, point C, I've taken a dashed green line and I've extended it past the particular y-axis and marked it as 2%. As I said, it's better you take it as 1% LEL, because that is going to be a safer value. You are being on a safer side. And remember, all these LEL and HEL will differ from gas to gas. Okay, one flammable gas to another flammable gas. So this particular point C okay, LEL, and your particular point D, HFL, when you are adding that third gas and the third gas being IG, remember, as we said, anything to the left of this line AB that is going from this side towards the y-axis contains this extra gas called inert gas, or IG we call it for short. As you're adding IG, especially the tanker guys will know, as you're getting IG, we are displacing O2, and therefore you're going from 21%, 20.9%, you're moving more and more towards 0% of oxygen. IG is replacing the O2 in your tanks. Okay. Now, that is why I've drawn these two, and you will see later on from the notes that are provided over here. Okay. These two dashed lines that I've drawn in my diagram, as you begin to add IG from 20.9, 21% of O2, as you're displacing the O2, what happens to these two theoretical lines? They are not actual lines. They are theoretical lines that have been drawn. As you keep adding IG, the dashed green line and the dashed blue line, they start curving towards each other. Okay, so let me indicate them by this green arrow, and the one closest to dark blue, let's use this blue line. Okay, so this dashed blue line will start curving in the downward manner. So whilst the dashed green line starts moving in the upwards direction, this dashed blue line will be starting to move in the downward direction. And as you keep adding IG, at about 11%, okay, now this is, as I said, is not a very correct diagram. At about 11% of O2, both these lines meet at point E, where you're going to have 100% LEL. Above 100% LEL, we are talking about LEL. This is 100% LEL. Once you go past this, you're going into the HEL region. Okay, so at 11% of O2, you are having 100% LEL. All that you require is this heat source, and you'll have a fire explosion. So when it meets this green line and this dashed blue line, when they meet at point E, that is how you're going to get this particular curve called the flammable range, flammability region, or explosive region. If you come anywhere in this particular region, definitely with an ignition source, you will have a fire and explosion. Okay, so once again, point D, point C, we've taken these theoretical dashed lines, the green line and the dark blue line. And when you're adding this third gas, anything to the left of this line AB, we are adding that third gas called IG, inert gas. As we are inerting our tanks or whatever, we are reducing the oxygen content. As we reduce the oxygen content, these two dashed lines, theoretical dashed lines, start moving towards each other. The one that is dark blue is curving downwards. The one that is green is curving upwards. They will continue, and at around 11%, look at this over here. Okay, that's why I said this is a more technically correct thing. If you draw E down over here, this is equivalent to 11%. This we have covered in the advanced firefighting course that we have done, okay, for our HTCW mandatory courses. Okay, at 11%, we know that we will definitely have a fire and explosion because it lies on this curve. Just like point D is lying on the curve, just like point C is lying on the curve, point E is also lying on this curve. And we now know how this curve is formed. Definitely one is going to have a fire and explosion because point E represents 100% LEL. And from point E, I've drawn a dashed line that is equal to 5% in volume. we will see the difference between percentage LEL and percentage volume. And as I mentioned, this is high 100% LEL. The 100% LEL is equal to 5% in volume. We'll see that also shortly. What is the difference between percentage LEL and percentage volume? Okay, so now everybody is clear how we get this flammable curve DEC. And guys, if you are going to give this type of explanation to the number of cross questions that can be asked on this diagram, believe me, you are going to be passed. No two ways about that. But please remember the correct thing when you are going to give the answer. Don't get confused. Yes, initially it might be confusing, but if you go through it a few times, you will be able to know it like the back of your hand. Okay? So any queries or doubts with regard to this flammability diagram thus far? Right. So, okay, now we've seen most of this flammability diagram and the important things. And now let's say the chief officer on board a particular tanker is discharging his cargo and a message comes from the office. Captain goes and discusses with the chief officer. They are taking us for dry dock after this discharge. So accordingly, just prepare the ship. Once discharge is complete, prepare the ship, gas free the ship and get it ready so that we do not waste too much of time going into the shipyard. Okay, captain's job ends there. Chief officer's job starts, his deck crew job starts. So also the engineer's work also starts. So now the chief officer has to gas free his tanks. He is discharged. He is put IG into the tanks. And now he has to get rid of that IG. He has to get rid of the residual flammable gas such that you're going to have 20.9, 21% of O2 into those cargo tanks so that he can send his men down to clean those tanks. You don't leave the tanks there as is. All those unpumpables in the form of sludge, etc., have to be removed. Okay, and the tanks made almost squeaky clean. There has to be cow, not just cow. Your tanks have to be after cow and all that. Then your tanks have to be, your cow normally is undertaken whilst discharging. Okay, and after all that, once the cargo is discharged, then they actually wash down the tanks with seawater, not fresh water, with seawater. Okay, and thus prepare the tanks for inspection, etc., and make it totally gas-free. That's where the chief officer is going to consider this diagram called the flammability diagram. And that's where these black dashed lines come into play. Now, I've marked certain dashed lines by a certain thing here, FA, HA, and IA. In the diagram over here, FA remains the same, but here they're having LA and HA as two different lines, okay? But it means one and the same thing. So let's take one line at a time. So now the chief officer's got his orders. He has to gas free his tanks because he has to clean his tanks. And therefore, he has to put in air and get rid of this particular flammable gas and that IG. Okay, so he could be very much into this. Normally, after discharging, you will definitely be in the HEL region. Okay, anywhere over here you can be. So we are taking this particular thing over here. We are in the HEL region, and if he is a completely inexperienced chief officer, let's say he says, all right, let's quickly finish off the job and let's start introducing air. Anywhere the flammable gases and the thing and the IG are going to be pushed out by that air. In that case, what is he going to do? He is going to follow this line, returning to 20.9, 21% of O2. So where is that line? FA taking you? It is taking you right through the middle of this flammable region. Whether my diagram or that one, it is going right in the middle of that region, that dangerous region. That's why it's colored red. Okay. If at that particular time, due to static electricity or any such thing, even a drop tool that can emit a spark, that will be more than enough to ignite that particular mixture, gas air mixture. Okay, and you will have a fire explosion. So nobody or no chief officer in his right sense will follow this particular line FA. Okay. Also the same over here, it's line FA. So both are one and the same over here. Then let's say he tells the chief engineer, Bada Sahab, I need more IG, because that is what you're going to do. You need to bring down the O2 levels. Okay, O2 level at point F, if you're going to draw it down, it will come up to about 5%. Generally, that is safe because you're far away from this flammable curve. We said anything below 11%. Okay, and they said initially you would have done this also in your firefighting course. Even 10% you are safe enough. But they wanted to be safer than safe, and that is why nowadays you're having it as 5%. 5% or lower, and that is why even in your IG panel on the in your cargo control room, okay, you are having a recording chart. So at any given time, that should not go beyond 5%, especially when you are discharging. Okay, so it should not go beyond 5% of O2. Right. So he tells Bada Sahab, I need more IG, so please give me more IG. Bada Sahab tells the first engineer stroke second engineer, just put the guys on duty. Okay, your normal watchkeeping duty as chief officer requires thing, because nobody is going to go UMS with the boiler and everything running. Okay, so engineers will start keeping watch, IG is going to be given, and more IG is given, and then you reach point H. That's where I said this line is wrong of mine, FI that I've drawn. So from point F, giving more and more IG, in other words, you're reducing your O2 less and less, and if you're going to draw this down to your x-axis, this is roughly about 3.5% of O2. Okay, and if you're saying, you're only looking at the O2 content and say 3.5%, this is safe enough here. Okay, if the chief officer says safe enough and he starts introducing air, then what is going to happen? From this point L, he is going to reach 20.9%, 21% of O2. But you can see that this line is very, very close to this flammable region. It's not region. Okay, very close to this flammable region. Okay, and any tanker guy knows that your O2 analyzer, when it is measuring the O2 content, is not spot onto that particular O2 content. It's slightly increasing, slightly decreasing. Okay, sometimes it goes beyond 5%. So let's say because of the slight fluctuation in this O2, it has gone to 5%. If it's gone to 5%, that means you're taking it to this point here. Okay. So in other words, this line would come back into this red region called the flammable region, the dangerous region. And because even though now at this particular point, when it's the 3.5%, we are outside of this region, that region can shift. In other words, this line can shift up or down. If it comes down, no problem. But if it goes up, then it's going to come into this particular region. So then you're going to have a fire and explosion. A lot of other precautions would have to be taken to prevent that from happening. Because this line is so close, here it is mentioned as line LA. In my diagram, it is mentioned as line HA. Okay? Because it is lying so close to the flammable region and may enter into the flammable region, this particular line is called as the critical dilution line. Okay, it's very critical. Okay, so this is the critical dilution line. No self-respecting chief officer is going to be satisfied with 3.5% of O2. He'll say, Bada sir, give me one more day here. Okay, just tell your engineers to bear with me. बाद में party हो जाएगा. ठीक है? So chief engineer also encourages his engineers, अरे party हो जाएगा इसके बाद में, and he gives more IG. He brings the IG down to point H, where if you're going to draw it down, say this is roughly 2.5% of O2. Okay, so from 3.5, he's reduced it further to 2.5%. And then if he introduces air at this junction, okay, he is going to follow this line down to point A. Okay, so here I've named it as I. Of course, as I said, it should have been further to my left over here, but okay. First and foremost, you're coming into the, here it is little higher. Okay, fine. You're not yet too much into that lean zone, too lean an atmosphere. But still, even if you're going to introduce air, okay, then you're going to introduce and come into that too lean an atmosphere, and then you're free to put right up to 20.9, 21% of O2. You can then vent freely. Okay, so this would be the normal pattern that the chief officer is going to follow. Line HA in this diagram, and in my diagram, it is going to be line IA. Okay, so this is the safest procedure that the chief officer will follow in order to prevent a fire and explosion. Okay, everybody clear? Any queries or doubts on the flammability diagram? Anything that is troubling you with regards to understanding the flammability diagram, whatever I described? If you are having a difficulty, I will explain it again. So please let me know now before we move forward. Okay, great. So I hope that if any questions are thrown at you in the orals with regard to the flammability diagram, you'll be very confident in taking it up. Okay, right. So why did we talk about this flammability diagram? We saw on the y-axis, we saw something measured in percentage volume. We also saw something called LEL, HEL. Okay, and therefore you have to have certain particular instruments to measure what is LEL, the flammable gas in a percentage LEL, and a flammable gas in a percentage volume. Now you have even your multi-gas detectors, but we still have around on ships your explosimeter and your tank scope. Your explosimeter is graduated or calibrated to give you a percentage of that particular flammable gas in a percentage LEL value, and your tank scope is going to give you the flammable gas that we just now discussed, the same flammable gas in a percentage volume value. Okay. Now, before going into percentage LEL and percentage volume, remember I said at point E is 100% of LEL, which is equal to 5% volume. Now, let us explain and understand what is the difference between percentage LEL and the difference in percentage volume. Okay, so why, one of the questions, why measure in percentage LEL and percentage volume? What is the difference? And this is the difference. Okay, so suppose this is your cargo tank carrying that flammable gas, fuel first, and now it is full with that flammable gas. That tank is 100% volume. Okay, 100% volume. Of this 100% volume, this black shaded area is equal to 5% of this volume. It's not to scale, but let's say this particular area that is shaded black is equal to 5% volume. This 5% volume is equal to 100% LEL, And that 100% LEL is what? Point E that is lying on that flammable curve, that flammable region. Okay, and it's putting you straight away into that dangerous thing, because point E is lying on this curve. You will definitely have a fire and explosion, because the amount of O2 is equal to 11%, and 11% is the minimum of the oxygen that is required in order to have a fire and explosion. Anything less than 11%, you are not going to have. Okay, so that is the difference between a percentage LEL and a percentage volume. Okay, everybody clear? Any queries or doubts on this?
Sir, can you repeat one more time, please, sir?
Okay.
Percentage volume.
Yeah. Okay. Percentage volume is compared to your cargo tank. This is your cargo tank. The entire cargo tank will be taken as 100% volume, because you're going to load your cargo into that. No, so they're always talking about volume over there. So this will be 100% volume of that tank. Of that tank, the 100% volume, if you take this shaded area, the black shaded area, which is equivalent to 5% volume, this 5% volume is equal to 100% LEL. And 100% LEL, we said 1%, 2% LEL, depending on which is the flammable gas. Hydrogen is having 4% LEL. If you are going to have that same gas at 100% LEL, which is 5% of that volume, then you are definitely going to have a fire and explosion, because we saw that is corresponding to point E on this curve. Okay, this is 100% of LEL, which is equal also to 5% volume of that entire tank that we are talking about. Okay, and since it is falling on this curve DEC, which is your flammable curve or flammable region, you will definitely have a fire and explosion. So that is the difference between your percentage LEL and percentage volume. Okay.
Understood, sir. Thank you.
Yeah. Okay. Right. So we have very little time. Very briefly, we will move on to the explosimeter. The explosimeter is very commonly called on board the ship, but the more correct name is combustible gas indicator, CGI, combustible gas indicator. Please note the word combustible, because that is what this explosimeter is going to be working. Okay, it is going to be working on the combustion of that flammable gas. Okay, so very quickly I'll go. Tomorrow again I'll be explaining the entire thing. So very quickly I'll go. Basically, your combustible gas indicator or explosimeter contains a Wheatstone bridge. Of the Wheatstone bridge, all the 4 resistors, if they are of equivalent value and a supply is given, then during that particular time, nothing is going to be flowing through the middle arm, and the Wheatstone bridge is considered as balanced. One of those resistors is replaced by a platinum resistance wire, which is coated with a chemical called a catalyst. That catalyst helps in the process, but does not take part, but does not change in its physical or chemical properties. That is what is a catalyst, or definition of a catalyst. So this catalyst helps in this procedure. What is the procedure? Is that once you start aspirating and drawing a sample of the flammable gas over here, this chamber that is heated up to a certain temperature already, thus making all these resistors equal in value. But when a sample of of flammable gas comes in over here, because of the catalyst, what is it going to do to that flammable gas? It will make that flammable gas actually burn on this element. This element, the sensing element, is a platinum resistance wire, as I said. platinum resistance wire is a PTC element, positive temperature coefficient, meaning when the temperature rises, the resistance also rises and vice versa. Temperature falls, resistance falls. So because this is already heated up to a certain temperature, we'll see what is that temperature tomorrow. Already the temperature is there, but now the gas has come, and because of the catalyst, that gas is going to physically burn on this element. That is why we said that this particular instrument is also called as the CGI, combustible. Okay, so that is what I said. Please remember the word combustible. Okay, so that gas is going to burn over here. Because of the burning of this gas, the temperature is also going to rise further than whatever the chamber was at whatever temperature. Because of this change of temperature, the resistance of this is going to rise. Okay, change. Remember, platinum is a PTC element. So it's going to rise. When it's going to rise, it's going to be out of sync with these other three resistors. Its value is going to be different. Because the resistance has risen, your Wheatstone bridge has become unbalanced. Because the Wheatstone bridge has become unbalanced, a current is going to flow through the central arm. The current is going to flow, the amount of current that is going to flow is directly proportional to the change of resistance, which in turn is directly proportional to the amount of that flammable gas that is coming and burning over there. So therefore, your galvanometer, this meter that is there in the middle, will be calibrated to give you the amount of that flammable gas in a percentage value. Okay, percentage LEL value. Okay. So once again, tomorrow, I went very quickly through this because we are out of time. I'll again explain it in greater detail tomorrow with regard to the explosimeter, also called as the combustible gas indicator. Okay, so today we will end our class here. Tomorrow we will continue and complete combustible gas indicator or explosimeter. We'll complete the tank scope. Then we will move on and complete the portable gas detection equipment. Okay. Right. So thank you very much for joining. Take care. And I'll see you tomorrow again at 11 a.m.